So in this problem-solving example, we're looking at something called proton beam therapy. So in this, we have a high-energy beam of protons that are fired at a tumor. So the idea is that the protons stop on the tumor and their kinetic energy is used to break apart the tumor's DNA, killing the tumor cells. For a particular patient, it is calculated that 0.1 joules of proton energy needs to be deposited. To create this proton beam, protons are accelerated from rest through a 10,000 kilovolt potential difference. What is the total charge of protons that must be fired at the tumor? And another way to ask this would be, how many protons do we have to fire? Since the total charge of protons and the total number of protons are fairly straightforward to convert. So first I wanted to maybe draw this out and say, well, how is this even working? Well, what you do is you could have a positively charged plate here and then have a negatively charged plate here. And the negatively charged plate has a hole in it, whose size I've exaggerated probably. And so we could add positive charges, i.e. protons. We could have a source of protons throughout. And so what would happen is we would see that these protons would have a force on them and would accelerate from the positive towards the negative plate. Now it's okay at this point that they could be kind of all over the place, because what will happen is they'll all experience the force, but only the ones that are aligned with this hole will get through. And so what you'll end up with is this beam on the other side of protons that have been accelerated, and they align just right so that they got through. And so we've got this potential difference here. Or delta V, and that's producing our proton beam. Okay, so that's the premise here of what we're doing. Okay, so now that we've got kind of a visual look at how this is going to work, knowing that we're taking charged particles, accelerating them through this potential difference, which we were told. And let's start working through some numbers. Okay, so how is this going to work? Well, we're looking at a conversion, right, between different forms of energy. So we're using this potential difference to produce kinetic energy. So we could say, well, our change in kinetic energy is going to be equal to the negative of our change in potential energy. Remembering that our conservation of energy states that, all our change in kinetic plus all our change in potential has to be zero. That's our conservation of energy. And that's going to be equal to negative Q and our potential difference. Okay, well, let's then solve for Q and say, well, Q is going to be equal to negative delta K over our delta V. And really, what we're looking at here is a delta K over the magnitude of our delta V. Right, and let's just think about that for a moment. Why is this in this case? Well, so protons travel through a decreasing potential. The protons are accelerating. Remembering that charges are going to be accelerated or not, depending on, or rather in which direction they'll go from what plate to what plate, depending on if they're positive or negative. So a potential difference will affect a positively charged object, opposite to how it affects a negatively charged one. So in this case, positively charged protons are going to travel, accelerate through this decreasing potential. Thus, okay. So that's just a little aside to get a sense of what the signs are. Okay. So back over here, we're going to go and solve for Q. And we've got a change in energy of 0.10 joules. We know that's the goal. We were told that's the amount of kinetic energy that we need. And we were also told that we have a potential difference of 10 times 10 to the 6 volts. And the 10 to the 6 factor you've got to carefully extract. We've got a 10 to the 6 factor there. So this is 10 to the 3 and then 10 to the 3, right, for the kilo and this. So we've got a factor of 10 times 10 to the 6 volts there. Be a little careful when you combine these kilovolts with a number that's also got a factor. So that's got to be carefully used. And so then we get our Q value. Well, it's going to be 1 times 10 to the negative 8 coulombs. Or another way to put it, we could say, well, that's 10 nanocoulombs. Remember that nano is a factor of 10 to the negative 9, so it's larger than that. So we've got 10 nanocoulombs worth of charge. Okay, so that's the total charge of protons that are needed. So we could then say, if we want to know, well, what number of protons is that? Well, we know that each proton has a charge of E. So 1.6 times 10 to the negative 19 coulombs. And so we could just divide the total charge that we have by E to get the number of, so it would be the number of protons. Okay. So I just want to do this another way as well. So, well, let's think about this a different way. So protons have charge E, and kinetic energy after this potential difference is going to be equal to 10 MeV. That looked a little crowded. So I'm going to rewrite this just below. So protons have charge E, and so the EK after delta V is 10 MeV, right? Because the delta V is 10 times 10 to the 6 volts, right, from up there. And then so it's really straightforward to go to electron volts once you have a potential difference when you're dealing with, especially dealing with a proton. And so we know the energy immediately. And that makes electron volts really useful. Now, let's say we still wanted to have this in joules. Well, then we could say, fine, 10 MeV, reminding ourselves that M, is this factor of 10 to the 6, right? So 10 MeV is going to be equal to, well, it's 1.60 times 10 to the negative 19 joules, right? So that's our amount of energy in 1 MeV, in 1 EV. And then the M part gives us this 10. So it's how many? So it's going to be 10 times 10 to the 6 electron volts. So here's our 10 MeV, and here's our charge. This is joules over 1 EV times this many EV. And so from this, we get that 10 MeV is equal to 1.6 times 10 to the negative 12 joules. Awesome. So that might actually, if you're familiar and comfortable with EV, that might be easier. It certainly is faster. Now, of course, we can also ask ourselves, what about the number of protons? And that's fine too. We just go and we can say the same way, right? We're going to go, well, total. So we've got 0.1 joules over the 1.6 times 10 to the negative 12 joules, no matter how you got there. And that's going to give us 6.3 times 10 to the 10 protons. That's a lot of protons. Okay, and we say, well, total charge. Well, that's 6.3 times 10 to the 10 protons times 1.6 times 10 to the negative 19 coulombs per proton. And we get a total charge value of 10 nanocoulombs. So there are two different ways that you can get to the same answer. And it's good to be comfortable with doing it either way, using electron volts, and then being able to convert between the number of particles and the total charge. Okay, and that's it.